Hello and welcome everybody to another edition of Algorand Developer Office Hours. I'm your host, Ryan Fox. I'm developer advocate here at Algorand. And today I am thrilled to have a double header on tap today. We're going to be learning about the Trailblazers Bounties program that's happening on Gitcoin, as well as take a look at the Algorand virtual machine. So today I'm joined by my colleagues, both from the foundation and at Inc. So Joanna Moran, she is head of European communities at the Algorand Foundation. Welcome.
Thanks, Ryan. I'm delighted to be here.
Thank you. As well as from Algorand Inc., I have John Gennady, head of applied research, as well as Paul Regal, and he is chief product officer here. Welcome to you both as well.
Hey, thanks, Ryan. And great shirt.
Thanks, Ryan.
All right. Thank you very much. All right. I want to get some quick introductions from each of you. And then, so in that, just tell us where in the world you're located, what you do briefly, and Joanna, why don't you kick us off, and we'll go to Paul and JJ after that.
Okay, thanks, Ryan. So I'm Joanna. I'm the head of European communities for the Algorand Foundation. I am based in Dublin, Ireland, and it's really lovely to be here because I've spent a lot of time, on the community side, and this is my first time kind of participating in the developer, the audience. So it's really lovely to be here, and I'm really excited to tell you about the Trailblazers program, the Bounty program.
Yeah, so I'm the chief product officer here at Algorand. So I'm focused on all things product and engineering related, making sure that we understand the market, we understand what the requirements are, we understand where the market's going, and then that we execute and deliver the right technology to support it.
And I'm the head of applied research, which in particular means that I'm focusing on building out better smart contracts, keeping them as fast as they've always been, but making them easier to use and maybe more likely to be bug-free.
Sounds great. Well, thanks for everybody. So John and Paul, we're going to have you guys take a back seat, and we're going to bring Joanna up here to the spotlight because I heard she's got $2 million that she wants to hand out in bounties. So why don't you tell us a little bit about that, please?
I'm here because we were so excited. We've launched the 2 million Algorand Trailblazer bounty program, and we really wanted to put something forward for our community that both developer and the non-developer communities could work on. We launched it in the middle of June, just 2 weeks ago, and we're bowled over by how the community has engaged with us. We launched this on Gitcoin. And our reason for doing that is, we wanted to provide like these bounties and provide a place where people could work on things at scale. And so, many eyes could get on our bounties and grow out our ecosystem. So to kind of give you, so it replaces the developer ambassador program. It allows, as I said, more scalability and better ecosystem management, like through Gitcoin. So it allows us to find out, either from the tech community or the marketing community, like what bounties you want to see there, and then post them to Gitcoin and get them reviewed really quickly, and actually, most importantly, get them paid out quickly. So the type of bounties that we have, as I said, they're like tech bounties, and they can be anywhere from beginner to advanced. And then the marketing bounties, you'll see bounties in like blog posts or video content, hosting events. We saw there's a bounty up there for hosting an event in China, and then introducing partnerships. And what that is in your ecosystem, you come across a really cool project and you think, oh gosh, this could be really, really great on Algorand. Make that introduction, we're like a team, we're limited. So like the more people bring, more projects into our ecosystem is good for us and good for the ecosystem. So, what do you do? Okay, so there's like, how do you apply? We've got the technical ones. So here is kind of an examples of tech bounties. So an open DAC contest. So this isn't actually you submitting a DApp, because obviously like it needs a lot more like, I guess, kind of financial support. It's actually like proposing dApps that you think will be good. And we're even like paying out bounties for that. Develop new framework integrations, PR improvements on Algorand. And we've seen like, a lot of interaction there. on Gitcoin. And then on the marketing side, you know, promotional podcasts, we got a couple in there last week. They're great. And then, as I said, introducing projects to the Algorand ecosystem, and that's through our grants program. And then we've seen a lot of our articles. So we're actually just reviewing all those blog posts. So thanks a million to everyone that's supported and made submissions. So how do you get on? So as I said, you know, we partnered with Gitcoin on this, and you need to set up your GitHub, which I'm sure many of you have, and then create a Gitcoin account. And then you can register for Gitcoin bounties. This, if you can see here, this is these are our bounties on Gitcoin. As you can see, there was many. Got really nice bounties for the Chinese market and Asian market. And then there are some tech bounties as well. So we'd love to see, you know, we want to kind of highlight, you know, the tech ones and get, you know, you as our tech community and developers, you know, get working on those bounties. Is there any questions that anyone has so far? Ryan, is there any questions?
Yeah, we've got a couple here. So let me ask you the first one. Robert asked, so who can submit a bounty? Who's eligible?
So anybody can submit a bounty. Oh, do you mean like to work on, or do you mean like to work on the bounty?
Yes, correct.
Yeah. So like, you know, if there's any tech bounties out there, you know, if you are experienced enough, then, you know, apply to work on that bounty, and our DevRel team they'll kind of approve you to work on those bounties, and you can go from there.
Great. Well, then what happens if they've got an idea about something that perhaps could be eligible to put forth as a bounty? Is that also available?
Sure.
I don't know if that was the question, but I'm glad we've got that one as well.
Yeah, no, that's a really good question. So, you know, we just launched 2 weeks ago, and we're, you know, finding our feet, if you will, with it. But, you know, the whole, you know, point of this is so that the ecosystem can grow out. You know, like if we're just posting those bounties there, then, you know, it becomes siloed to just our organization and the Inc. So, you know, we in time want to see our ecosystem posting bounties and paying out in algos. So that will be, you know, like the plan, and not in a couple of months, in a couple of weeks. We hope to see that.
Outstanding. Well, who sets those bounty sizes? I know you showed kind of a list of the different bounties that we have available today, and who is selecting how much those are worth?
Yes, and that's also a really good question. And there is a little bit of trial and error with that. You know, you put some bounties out there and, you know, they're not getting any bite, and you're like, oh, I think we might need to up that one. You know, if it's a piece of, you know, tech or code that needs to be done, you know, we can kind of like, you know, review it and then up that amount. Or, you know, people just aren't interested in work on a certain, you know, topic. We've seen that in a couple of our marketing bounties. So it's a little bit of trial and error. So bear with us. You know, we're a work in progress, and trying to just make it as better and as fruitful for the ecosystem as possible.
Wonderful. Well, that's good. Maybe just one kind of clarifying question. You know, is the concept of this like a hackathon, or is this like we've set this body of work and we want this done, and we'll have it then integrated into the code base or into the marketing plan or something along those lines? How do you envision this?
So, like, as it's over 2 years, you know, there's that kind of, we've set out, you know, that budget for it, and I guess it just, you know, everyone kind of knows blockchain can you know, everything can happen very, very quickly. So, you know, over a 3-month period, we might need very different things from the start of the 3 months to the end of the 3 months. Great. But, you know, we have our ecosystem teams are evaluating, okay, well, what's kind of missing? What do we really need in our ecosystem? And we'll probably see a little bit more kind of prescriptive work going on with the bounties.
Okay, good. Well, John, thank you very much for introducing the Trailblazers bounties on Gitcoin. Remind us again, how do we get connected specifically to those bounties? Where within this Algorand ecosystem can we engage with them?
Sure. So this is a QR code to get to our Discord channel and Gitcoin Bounty channel. And any questions that you have, Autumn, Haichao, and I will also be there to answer any questions that you have, and obviously all the DevRel team that are here. Anna Mikel, who's also our DevRel on the foundation side, is there to answer any questions.
Outstanding. All right, Shohana, thank you so much for introducing us to the Trailblazers bounties on Gitcoin. We're really excited to do that. We're going to bring up Paul and John at this point. All right, hey, welcome back, Paul and John. Thrilled to have you guys here. Sure, Algorand, we're committed to innovation. We're always focused on performance, interoperability, smart contracts, and we are committed to remaining fully decentralized public permission protocol. So I know that you guys are going to tell us about our new approach to designing, developing, and deploying smart contracts on Algorand using the forthcoming Algorand virtual machine. So how about if we just pass that over to you, Paul?
Yeah, absolutely. So I got some slides to share. Now I know this is a developer office hour, so I've got some slides, but we will also spend a significant amount of time just sort of walking through code and examples to really get into the tech itself. Okay, so this talk from myself and JJ is really focused around the Algorand virtual machine. We're going to hit a couple things. I'm going to very briefly talk about, at a very high level, our smart contract strategy and where the AVM fits in. Then we're going to talk about our most recent release, the AVM version 0.9. It is in BetaNet now. It is slated to be in mainnet tomorrow. And so this is sort of hot off the presses, walk you through the features that are coming in AVM 0.9, and then do some code walkthroughs as well with JJ. And then I'll just give you a little bit of a taste of what's coming in 1.0, which we expect to be delivering here in Q3. And then, of course, we'll get to some Q&A along the way. And then particularly in the code walkthrough, I think JJ will talk about it, but I think that could be more interactive during that section than just a monologue. Okay, so from a high level, folks, our smart contract strategy here at Algorand, it's not complicated. We are looking to have powerful, fast, inexpensive, and easy smart contracts. Two of these properties are delivered by the protocol itself. The protocol is fast. We operate at over 1,000 transactions a second. We are currently in the middle of a project to move that from 1,000 up to 10,000 and then up beyond that. And so the chain itself is fast. What that means is our smart contracts have to basically at the same speed as anything else on the chain. And so if the chain can max out at 1,000 transactions a second, we want our smart contracts to be operating at that same speed. Similarly, the cost of the chain is also driven. Cost of the smart contracts is driven by the underlying properties of the chain. Our transaction costs are 1,000th of an algo, 0.001 algos. This is true both for simple pay transactions, but also for smart contract transactions. And so that's kind of the fast and inexpensive piece. Is it inherits these properties from the chain because our smart contracts are at layer 1. Really, the two big things that we will continue to iterate inside of are powerful and easy. Our goal is to make an execution environment that is as powerful as any other smart contract platform on the market, and easier to program in. And what that means is we need to be able to, you need to be able to write smart contracts in mass market languages like Python, for example, or languages that are JavaScript like Reach, if you've seen Reach. Which has a bunch of other very, very interesting properties as well. And so to deliver on the fast and inexpensive, this is just a constant focus of Algorand, is to continue to make our chain faster, continue to make it operate more efficiently. But to deliver on powerful and easy, we had to have the right underlying framework to power our smart contracts to make sure that we could continue to move it forward. And that is the Algorand virtual machine, or the AVM. This is really the key to our strategy of being able to continue to provide power while also enabling ease. So when you think about the framework, like the mental model for our smart contracts, you write your languages, you write your smart contracts in a higher level language, such as Python, such as Reach. Those are then compiled down into bytecode for the Algorand virtual machine. if you're thinking, hey, that sounds similar to the Ethereum model where you've got, Solidity, or you've got Viper, and it compiles down to the EVM, you're right, it is a similar model. It's a very simple model. It's tried and true, and it's a proven model, and we're using the same thing. Our AVM is a little bit different in that it is faster, it is cheaper, but it provides similar power in the execution environment itself. And of course, using this model allows both innovative and accessible language. We talked about Python and Reach, but it also allows a really clear framework for advancing the languages that are used to write smart contracts, because you just have to target the underlying Algorand virtual machine from whatever higher level language you're using. And so you can imagine a world where the LLVM stack is integrated in and can compile down onto the AVM. There's a language called Clarity, which we are actively working at here at Algorand, that language is also used by Blockstack to write smart contracts. And that is a more decidable, security-focused language. But really, you can imagine anything. In fact, if you're out there looking at grants or other projects to do on Algorand, taking on a big project like bringing LLVM to Algorand, I think would be a noble cause for our community. So that's at a high level. It's a simple strategy. We're going for powerful, we're going for fast, we're going for inexpensive, and we're going for easy. We're delivering that through the Algorand virtual machine and allowing higher level languages to compile down into it, starting with Python and Reach, moving to Clarity, and then looking for the community to bring larger and more languages to the ecosystem. So now I want to get into specifically the Algorand virtual machine 0.9. So this is coming in the protocol version 2.7.1. Again, that is in BetaNet now and will come to mainnet tomorrow. So we're going to talk about the feature highlights. The theme here is what the themes are always going to be for our Algorand virtual machine: more power, better experience, and easier. So I'm going to talk about these things one at a time, and then we're going to have JJ sort of walk us through the code. By the way, if you are brand new to the Algorand ecosystem, this presentation is not going to go over sort of base capabilities of the AVM, the 100 and whatever opcodes, the how much storage you get, all that kind of thing. This is really going to talk about the deltas between what was available previously and what's available in this release. If you want to dig into sort of like, hey, I'm brand new, let me dig into AVM, I suggest going to our developer site where you can read about the AVM there, and you can kind of get into the details. It's developer.algorand.org. So for AVM 0.9, the first big introduction of features is we've introduced functions, looping, back jumps, recursion, effectively arbitrary jumps in your code. This is powerful for a number of reasons. You guys are developers, you understand that it just makes simpler code when you're writing it. But when you're talking about code on the blockchain, you're always concerned about the size of that code because it's got to be stored on the blockchain. It's got to be accessed quite frequently. And this allows you to write smaller programs for looping, not just add additional functionality and features using things like functions and looping. The second big change that we've made is exactly around program size. So the current limit on program size is effectively 1 kilobyte. In the new release, we can expand that code space up from 1 kilobyte all the way to about 8 kilobytes. Now, I'll be honest with you guys, we have a number of projects now that are writing dApps and smart contracts on Algorand, and they're everything from sort of order book style, decentralized exchanges, to AMMs, to lending protocols, to no-loss lotteries, and all of these folks are able to fit their programs into these 1 kilobyte sizes. However, they do have to spend a lot of time on optimization. And as you know, and I know, optimization is great, but even better is just writing value-adding code and not having to go back and optimize it. So this expansion here from 1 kilobyte to 8 kilobyte, I wouldn't think about it as, oh, now I can write this thing I couldn't write previously. I would think about it as, now it's easier for me to write this thing, and I don't have to spend as much time optimizing it. So a big increase here. We've heard from a lot of the folks building that this will make their lives easier to build their dApps. We've also combined the state key value pair limit. So in Algorand, for your state, for your smart contracts, it's a key value pair. We have previously had 64 bytes for the value, 64 bytes for the key. And we've combined those limits and just said, listen, you've got 128 bytes to use, regardless of how you use it. So you could use 1 byte for the key and 127 bytes for the value as an example. It's another way that we can allow larger programs, more complex programs, more state inside of them to ease the experience of building smart contracts. We've also introduced contract-to-contract composability, specifically via transaction groups, shared scratch space. So we have transactions. We also have transaction groups. If a transaction is in a group, that whole group is guaranteed is atomic. So either all of the transactions in the group will execute, or if one fails, they will all fail and nothing will be applied. In using this transaction group model, you can imagine a scenario in which you're calling many smart contracts in each transaction in the group, and then using a value that has been outputted by a previous smart contract call in that group. And this allows you to use that value from the previous smart contract that's called and really sort of chain together these contract calls for much more powerful composability for when you get into more complex dApps. This has been really well received by folks who are building those kinds of applications. Similarly, we are adding composability across transactions inside of a transaction group for newly created assets like Algorand standard assets and smart contracts. So this is a thing because the way that our globally unique IDs are created for ASAs and smart contracts is effectively there's a counter on the transactions. So when a transaction gets included in a block, we can guarantee that the counter for the transaction in that block is globally unique. The problem with that is that you then have to wait. Like I'm going to create an ASA, I got to wait for it to hit the blockchain, include it in a block. Okay, now I've got an ID. And while you can still write your programs, it does make this sort of like, okay, wait for the block, then get the ID. This functionality allows you to get that ID from an ASA or a smart contract created in a previous transaction in that transaction group without waiting for it to hit the block, which again just makes composability much easier. And streamlines the smart contracts that are being written. This next one here, we went crazy on the mathematical precision. In the DeFi space, precision is important, and the number of bits out to which you can do math is quite important. And so we have added a bunch of math opcodes, but actually allow mathematical precision out to 512 bits using byte slice math. This is interesting. Even other blockchains, Ethereum, for example, is at about 256 bits. In fact, exactly had 256 bits. So we can be even more precise inside of Algorand should that be needed as people build out their various DeFi applications. And then the last one is really less about the developer experience and the power of the smart contracts and more about your user experience. Inside of this transaction group, we have enabled fee-free transactions. So a quick example, if a transaction group has 5 transactions, let's say hypothetically the fee was 1 per transaction, 1 unit per transaction. That means the total fee for that group is 5. The protocol now does not care how that fee gets paid inside of that transaction group. So for instance, 1 transaction could pay all 5, and then the other 4 could literally pay 0. And so if you're building applications, you can structure the way people interact with your application to always be fee-free for your users as long as they are interacting with your smart contracts and your dApps. Really powerful feature, again, layer 1 primitive, where this is built into the protocol. You don't have to build some additional fancy smart contract to sort of manage meta transactions or fee-free or trying to reimburse. This is directly in the protocol and simplifies it from a developer experience and allows you to offer a really great service for your users. And as we all know, the fees are super normal in the blockchain world, less normal outside of the blockchain world. And so as you bring in more and more users to your application and you start jumping user groups from blockchain native out into people that maybe aren't as experienced in the blockchain, fee-free transactions are going to become an important part of that. So we're really excited to offer that in this release as well. So that's from a high level, those are the big pieces of functionality that are being added to the AVM in this release. I'd like to pass it over to JJ now, who's going to dive into some details specifically around the code and how we've implemented, how to use it.
All right, so I'm going to walk everyone through the additions we've made. I've focused mainly on the things that are maybe the largest conceptual difference from what we did before, and that's the addition of functions and looping. So there's a lot of talk of the phrase Turing complete. I'm going to avoid that phrase because it means something about the language, but it doesn't really mean anything when it comes to the execution environment. And there are still limits in place. But what I love about these kinds of additions is they allow you to program in a way that is more like you've been taught. If you've been thinking about programming well, then you've been thinking, oh, I should decompose things into functions. I should write a loop to do this in one place and get it all done correctly. And before you couldn't do that. You had to duplicate your code over and over again. So with the addition of functions and looping, I think what I'm most excited about is, well, I like the fact that there's going to be some savings in code space, but I'm very much very happy about the fact that it lets us use some sort of more traditional software engineering, principles to write cleaner code. So the first thing I'll do is introduce you to. So I should first say, when we say functions, Teal is approximately a one-to-one mapping to the AVM. So a Teal instruction, a Teal line, compiles down to 1 byte code, possibly with some immediate operands. So when we say we've added functions, what we really mean is we've added the support in the AVM to allow a language to have functions. So you'll see it expressed in Teal as something that looks an awful lot like some jumps and some more jumps. But you may see it expressed in other languages like Reach and like what we're planning on doing with PyTeal, where it actually looks an awful lot more like a function. So what you're going to be seeing now is the underlying support that allows that to happen. So this is kind of my Bootstrap framework that I write when I'm writing a new app. So it handles a bunch of on completion things. If you're familiar with the Algorand ecosystem, none of this has changed. Apps still have these completion enums and so on. They're not terribly relevant to our discussion. What is relevant is what happens when you get here. Surprisingly enough, it's the handling of a no-op, which is where your main code is. You may be familiar with this if you've written apps. So in this example, I wrote some drop-dead simple skeleton code before I write any code for you, which says if the first argument to my application is the word triple, first argument is triple, and they're equal, then I'm going to jump to the triple label. And that's where you might have written code like this sometime. If you need to, for example, write an app that, obviously I'm making a trivial example here, where you're checking to see if the first application arg is 1/3 of the second application arg, you would take the first argument, convert it from bytes to an integer, multiply it by 3, and then grab the second application arg, convert it to an integer, and then see if they're equal. That's perfectly fine. And in fact, you might not even use a function for this even now that you can, because it's only in one place. But it gives me a really simple place to show you how you would write what we're calling what look like functions at the AVM level. So let's suppose you wanted to write a function called triple arg. So you would make a label. You would now spend a little bit of time thinking. You would say to yourself, what's going to be what's going to be the discipline that I use when an argument comes in on the stack? I'm going to triple it, and I'm going to put it back on the stack. So it's almost like you're building a new opcode in Teal. So if I expect my argument to be on the stack already, and it's bytes, I can convert that argument to an integer. I can load a 3. I can multiply. And then I've got my answer on the stack. And so the question is, how do I get it back to my caller, someone who came into this subroutine? I say retsub. Well, why is it called retsub? It's because when I jump in here, I don't just jump to this routine. I call sub this routine. So my highlighting is not great. I'm going to get rid of the underscore so that it highlights nicely. Okay, so now I have a routine called triple arg. So if I load a byte here that represents an integer, this will convert it, multiply it by 3, and then return it. So this is just like the absolute most basic function you can possibly write. By itself, this isn't super interesting. Let's move on to some interesting stuff. So let's suppose that you need to convert a string that contains a string representation of a number, like the ASCII digit 5. You need to convert it to the number 5 so that you can multiply. Let's look at how there's two very different ways you can do it. We've added support both for back jumps, which give you loops, and for recursive subroutines, which gives you recursion. You can write this function either way. I'm going to walk you through writing it those two different ways. Some people will prefer one, some people will prefer the other. Let's do an iterative solution first. So we're going to take something where, so check out this simple compare function. This is not, of course, very interesting. It takes two application args and it checks to see if they're the same. But what if you pass the first one in as a string? So if you're familiar with goal, you might have passed in app arg stra 456, for example. And you pass the second one in as an int. So you pass in 456. So if you did this, this comparison would not return equal. Because in fact, what would be passed on the network is these 3 bytes, 4, 5, and 6 as the first argument. And then actually, I guess it would still be 3 bytes. Let's make it smaller so it's more obvious what's going on. This would be passed as the single byte, the ASCII 5, which turned out to be the number 53, I think. This would be passed in as a single byte that is the actual binary 5. And so those two bytes are not the same. And so this would return false. And your whole, if you return here, your TEAL program would fail on purpose. You would say that they're not the same thing. So what if you wanted to write something that would convert this string? So I want to be able to say call sub c to I. Take a character and turn it into an integer. So notice that c to I doesn't exist. So let's start writing it. C to I is going to look like that. Let's see. I want to make sure that I don't have typos, so I have some of this written down for myself. So I don't want to confuse you. It's a little too hard for me to go back and forth between this and a shell and actually show you this stuff being submitted to the network. But rest assured that this has all been submitted to the network and works properly. So what would C to I look like? It needs to grab the. C to I is going to take a string. Whatever's on the stack currently when C to I is invoked. It's going to look at the top thing on the stack. It's going to be a string, and it's going to take the first character from it. So how do you do that? Well, we have a get byte operator that expects to find the string and then the byte you want, and then you invoke it. So this will get the 0th byte of the string that's on the stack. So notice I called C to I after loading the application arg. So this loaded this string 5. It takes the 0th byte of 5. There's only one byte, so the 0th byte is the first one. So it's got the ASCII 5. It's got however 5 is represented. And let's pretend that we don't know ASCII, so we don't know that's 53. So instead, once we figure out what that byte is, let's find out what how the byte 0 is represented. So we'll take the 0th byte of that thing as well. And so now we've got two things on the stack. We've got the first byte of the 5, and we've got the first byte of a 0. Well, the first byte of a 0 is however ASCII represents zeros. We don't know. It happens to be 48. But let's say we don't know. So let's subtract them now. So now if this had been, so whatever ASCII 5 is 5 higher than ASCII 0. So this gives us the actual number 5, and we're done. We can return from the subroutine, and now C to I. Were I to submit this thing to the actual network, this would return true now. I send it the string 5, I send it the integer 5, and I've converted it. So slightly more interesting function, but still not terribly interesting because this doesn't work, right? We've only written something that looks at one character and converts it. So let's write something that converts any number of characters so that you could send a string 51265 and it converts it to 5,165. So first I'm going to write a little helper routine called lead digit value. And I'm going to show you why we break things up into functions, because I'm going to use my existing C to I function in this new routine. And I'm also going to show you a new piece of math that we've added. So this is called lead digit value. So the idea here is that if I pass in 2,326, it's going to take the first digit off, 2, convert it to a 2, but based on the length of the whole string, that it's 4 digits long, it's 2,163, I'm not going to return 2, I'm going to return 2,000. So this is a little helper routine that takes off the first digit and gives it back, but also tells me how big it really is in base 10. So I'm going to start doing something that I think is very helpful when working with a stack machine. And I'm going to start annotating, I'm going to start commenting my code with what the stack looks like when when I start calling this routine. Let's suppose I had called this routine with the string 512. If after I dupe it, I've got 2 strings, 512. You'll find that you very often dupe something so that you can operate on it without losing what you previously had. We already know how call sub works. Call sub replaces the thing, since we just wrote it, and we're really good at this stuff. So so it works properly. That means that 512, it takes the first character and it turns it into its integer representation. So I'm going to write it here without quotes. After doing call sub C to I, my top 512 becomes just the number 5. Then I swap them. So I do 5, 512. Then I figure out how long is that 512 by using the len operator. Oops. So the 5 is still there, but the 512 has become 3. Then I subtract 1 from it by first putting it out there. Then I do the subtraction. This becomes 5.2. Then I put a 10 on the stack. 5, 10, 2. And now I can use a new operator for exponentiation. 10 to the second is 100. So that 10.2 becomes 5,100. I multiply them, and I get 500. And so that's the thing that's being returned from lead digit value. So now perhaps it's clear what I meant when I said lead digit value's job is to take the first number, but actually return how much it's actually worth in base 10. Now that I have that, I can write the routine that you've been waiting for, which is oh, I'm sorry, I did the recursive one first. I think I told you I was going to do the iterative one first. This is the recursive one. So now I'm going to write something called A to I. This thing is not C to I just takes one character. A to I takes a string of ASCII. And it uses those routines that we've built, C to I and lead digit value. So the first thing it does, let's again imagine we pass in 512. We dupe it, we get 512, 512. We take the length of the top item. Now we have 512.3. We put a 1 on the stack and then we compare it. We're trying to find a base case for our recursion. If this thing was only 1 digit long, then we could just use our existing C to I code. So if this thing were 1 digit long, we would stay here. We would stay inside of this little jump here, and we would call C to I, and we'd just return what it says. So if we had been called with, like, let's say the string 7, we'd basically be done. It's only 1 character long. We can call C to I and be done. But unfortunately, we called it with 512. 512 is longer than 1. So this BZ is going to jump. It's going to jump to longer. Longer is the other half of our recursion, where we have to break our problem down. We had 512. We dupe it, get from 512 to 512. We call our subroutine that we already wrote lead digit value. So now we have 512 as a string and the number 500 as an integer. We swap them, dupe them, we take the length. We put a 1 on the stack, swap them. Unfortunately, you have to do a lot of stack manipulation to get things just right for calling these operators. And then we take a substring. So here's the key point. We got the 500 out of the 512. So now we want to take a substring of 512 to only do the 12. So now we have 500 and we have the string 12. Well, now we can call our subroutine A to I, the one we're actually writing right now. We can call ourselves recursively. So if we've written it right, and that's sort of the way you think about recursion, you sort of assume you've written it right so that you can call yourself on smaller versions of your problem. So the 12 string becomes the 12 number. Then we add them together, and we actually end up returning, I should put it here, we return 512. So now this thing shows off a few things. First, it shows off recursion. It shows off how you can now you can decompose problems into small functions that get things that are reusable. So we've reused our C to I function. We've reused our lead digit value function. We've done recursion, and we can convert any number written as a string into the number as an integer. Okay, so that demonstrates how you write. There's some other things that I like about this style of writing functions in Teal. Notice that we never touch scratch space. By never touching scratch space, you know that the functions you write can be called from anywhere without mucking anything up. Even if they're called from some function that is using scratch space, since you're not going to mess with the scratch space and you're going to leave the stack the same way you found it, you know that they're very that's a very reusable way to write your functions. I've started calling them mock codes instead of opcodes. They have the same properties as opcodes. Opcodes don't mess with the scratch space. They just manipulate their arguments on the stack, give you the result on the stack, and then they return. I think that's a good style for writing functions in Teal, but you don't have to. Teal is one-to-one with the AVM. The AVM is a bytecode language runtime. You can do things differently. So let me show you how to write similar code, but in a more iterative style. I'm going to plop the whole thing down and show it to you all at once so that we don't take a ton of time. This is another version of A to I written in an entirely different style that uses the fact that we can now do back jumps instead of using the fact that we can do recursion to get the job done. Here, when you do things with iteration, I find it a little bit easier to use a different style that isn't the mock code style. In other words, this is going to use scratch space to get this job done. And so it's very important here that you comment your code and take good care to assign certain variables to certain scratch spaces and always use them the same way. So here I've decided that scratch space 0 is going to be where I hold the string argument that I'm given with. So when I call A to I, which is A to I iterative, it takes a string 512 and immediately stores its argument in scratch space 0. Then we're going to have an index variable, what would be in a higher level language an index variable. Instead, we're going to treat scratch space 1 as the place that we're going to have an index that we're going to walk along the string. So that we're going to put that in scratch space 1. We're going to start at 0 though. And we're going to accumulate our answer. Our answer is going to start at 0. If someone were to pass us the empty string, we want to be able to return 0. So we're going to start our answer at 0. So in a high-level language, this might be called the sum. In a high-level language, this might be called the index, and this one might be called arg or s or something like that. But we just have to remember to use load to pull them out. So now we're going to write a loop. We're going to load 1, and remember that 1 is our index. So we're going to take our index, and then we're going to take our argument. We're going to find the length of our argument, and we're going to see if our index is already as large as or larger. And of course, we could potentially have written just equal here because we're not going to pass it, but I always like to be safer and use greater than or equals. If we're past the end of the length, then we know that we're done. So B and Z, you can think of this as, I almost think we should rename this opcode to BT for branch true. If this is true, then we're done. And that means that we load 2, which remember that's our answer, that we started out with 0, and we ret sub. So if we're already past the end of the string, which would be weird since we just got called, but if an empty string, we would immediately return 0. But we're probably not. Probably instead, our index is 0, and our string might be 4, 5, 6 characters long. So once again, we load our answer. I shouldn't say once again. For the first time, we load our answer, and then we prepare to whatever we've currently got as an answer it's now going to get multiplied by 10. Now at the beginning that's 0, so that's not very interesting. But think about what's going to happen as we walk along the string. If you're trying to figure out what 512 is, we're going to pull off the 5. First it's going to be worth 5. Then we're going to realize as we walk along the string, oh, that 5, it's actually 50. And then we're going to walk further along the string and we're going to say that 50, it's actually 500. So we're going to multiply our current answer by 10 and put it back, store it back away. Then we're going to grab our string argument again and our index, and we're going to get that byte out of the index. So we're going to, the first time through, it's going to take the first character off. Like remember our 512, it's going to grab the 5. Then I got a little cheesy here, and instead of calling my C to I function, I just subtracted 48. Now that we know how that works, if you've got an ASCII byte and you wanted to convert it to its digit value, you can just subtract 48 from it. So that's what I did here. So I pulled the first ASCII byte off of 512. It's 5. I subtract 48 from it, and I get the actual integer 5. Then I add that into my answer. So I had previously multiplied by 10 to get stuff out of the way. At the beginning, that's not very meaningful, but later on, the 5 becomes 50, and if it's 512, the 1 gets added in. So I add in single digit, and then I increment my index. I load my index again. I increment it by 1, and I put it back, and then I loop back to the top. This is all it took for us to be able to do all of this in Teal, the ability for this branch to be legal. It used to not be legal. You could not jump backwards to this loop. So we can jump back to the top, and again, we go through, we try to index along the string. Eventually, we're going to get to the end, and we're going to jump out of it, and we're done. But as we go, we're going to, each time we see a new digit, we're going to multiply what we've got by 10 and add in the next one. And so this is an iterative solution where you don't have to think so hard about how recursion works, but you do have to think a little bit harder about where you're going to store your variables. So that gives us 2 sort of interesting functions.
The one thing that I want to add on top of what JJ just showed us is really, I mean, JJ we're exercising the AVM itself using Teal, which in some ways you can think of as sort of syntactic sugar on top of AVM bytecode. What's great about the AVM model is that in a lot of instances, you don't have to think at this level at all. So if you're using something like Reach, where you're writing in this higher level JavaScript-like language, the Reach compiler is the one that interfaces with the AVM. And so from your perspective, you just write your loops as you normally would, write with your JavaScript-like language, and the compiler does the work of fitting it down into the AVM. I know there's a lot of folks out there on this call that like getting into Teal, and we're all about that. But if you're thinking, man, this seems at a lower level than I'm used to, it is, and you don't have to do this. You can use the higher level languages, and those compilers will take care of this for you. So just to recap, these are the functions we talked about. JJ really went through the first one, which is functions, looping, recursion, etc. Really, really powerful, not just for writing directly in Teal, but also for compilers that are using Teal as well. So let's talk about the 1.0 preview. So first of all, this is a Q3 target for us to release. So this isn't like a year out. One of the things we take pride on is really pushing out our features and improving at a rapid pace for our users. The themes, you can get used to these. If I had more AVM releases to talk about, you would see the same themes on those releases as well. There's 3 big things here. One is actions from smart contracts. So currently the smart contracts have a bunch of logic, and at the end of the day, they approve or reject transactions. This feature will allow you to create and send, we're calling them actions, directly from the smart contracts, which includes algos, which includes ASAs, and some other actions. You think of it like sending transactions from smart contracts really opens up, or at least makes it more efficient and the user experience a little bit better for dApps based on our smart contracts. The second one is escrow authority. So if you are really into the Algorand smart contracts now, you know that if you want a smart contract, a stateful smart contract to have authority over an account, you have to take a stateless account and stateful contract and weave them together. This update will allow you to have direct control over accounts from your stateful smart contracts, and in fact, more than one account. So really simplifying, again, the way these apps are put together. And then finally, we're going to continue to increase the power of the AVM. And in this case, it's going to be opcode budget. So we talked about properties of the chain. The speed of the smart contracts must match the speed of the chain. So we operate at over 1,000 transactions a second. Got to have that for the smart contracts, which means we have a budget around the opcodes that can be executed inside of that time, basically compute guardrails. We're going to really start working on those guardrails to really loosen them up. So for example, opcode budget specifically, we're looking to 10x the opcode budget inside of that 1.0 release. And again, this isn't I mean, from my perspective, when we're talking to users and seeing applications being built, these applications are getting built. The top, most interesting applications on Ethereum are getting built on Algorand, and they're operating within the current budgets. But when we think about, just the way of computing is that it's always more compute, it's always more storage. We want to make sure that we can keep up with any new functionality or any new uses out there. And one of the ways we're going to do that is by increasing this budget. This is a particularly hard one, just from in some ways, because we have to use, basically I'm saying, I'm going to allow you to use 10 times more compute, but I'm also going to continue to run at 1,000 transactions a second. And so we've got to kind of match those opposing forces in ways that make sense for everybody. But we're excited about it. And these three pretty massive features we expect to be inside of Q3 for our 1.0 target. And with that, Ryan, I'm going to pause there, and we can answer questions directly, or we can continue answering, the way we have been. I'm up for anything here.
Sure, I've got one question, and this is probably forward-looking a little bit, but tell us a little bit about if the AVM will deliver an equivalent to an ABI to interact with smart contracts.
Yeah, great question. JJ, you want to take that?
Yes, I guess is the short answer. We are developing an ABI. It is kind of what you would expect in the sense that we, will allow you to declare somewhere off-chain what methods you take and what types you take, and then it will be the job of the contract to actually obey the API that you claim to obey, or else your code's not going to work. So that is forthcoming. Some of the things we need to work out beyond, let's say, the Ethereum API is in the Algorand world. You sometimes use multiple transactions to get work done. We have a nice feature that allows you to do atomic transactions, lets you have multiple transactions, and sometimes to call an app properly, you need to use those groups. And so our ABI needs to be able to specify that information as well. Call this app with this additional transaction, and you'll get what you expect to have happen. So that's the bit of work that remains before we're going to publish that. But I expect we're going to publish in a prototype version of that within a week or two.
Well, great. I think that's going to wrap up our Q&A. Thank you to the audience for asking wonderful questions. Thank you, JJ, for answering those, and Paul, vice versa, as you guys were swapping back and forth. I think Johanna is still on, and I'm going to invite her back to stage, and we'll wrap it up together here. Here she comes. All right, Johanna. Well, thanks very much to everybody who was able to join us here on Algorand Developer Office Hours once again. Johanna, thanks for telling us about the bounty program on Gitcoin.
Great, and thanks so much, Ryan, John, and Paul for inviting me on to your office hours. It's great. And
to Paul and JJ, thanks to you both for joining and telling us about the forthcoming AVM. We're really excited to get in there and start working with that.
Absolutely.
Great. Remind us once again, guys, where is the best place to connect with you guys and learn more about the AVM and participate in that as it comes out?
Yeah, definitely on Discord is a great place to go. You can also go to our forums. And with the release tomorrow, all of the documentation will be up on the developer side as well. That's developer.algorand.org.
Outstanding. Well, thanks everybody for joining this episode of Algorand Developer Office Hours. We'll see you again in a future week.